Poisson distribution. Now this is a distribution where the outcomes are still binary. Again, we are talking about success, failure, etc., etc. I mean, yes, no kind of an experiment. But in this case, the probability of success is very, very small. That means we are talking about rare events. Let's say seeing accidents on road in front of us, or maybe thunderstorms at a place in Rajasthan, etc., etc. So these are all rare kind of events. That means there is very little chance of such events to happen. Let's take an example. Suppose I am sitting in a room and looking at the ceiling, and I'm imagining an event where the ceiling fan is falling down. Fan is falling down on me. And from my own experiences that I've heard from my friends, let's say that the rate at which the fan crashes down is 0.19 per day, right? Rate at which. And this rate is known as lambda in your Poisson distribution. And lambda is nothing but number of times an event happens multiplied by the probability of that event happening. So let's say I wish to simulate the number of times the fan falls down for the next 30 days. So I have to generate random numbers from a Poisson distribution. How many random numbers do I need? 30. And the parameter of the Poisson distribution here is 0.1. Remember, the first argument is always for all these R functions. The first argument is the number of random numbers, and the second, third, fourth, whatsoever arguments that follow are the parameters of the distribution. In binomial distribution, we had two parameters which were n and p. In Poisson distribution, we have only one parameter which is your lambda. So let's run this. So on the first day there is no event happening, second day no event happening, third day no event happening, fourth day there is a chance that the fan will fall down once, and so on. So since these are rare events, you will very rarely see a 2, 3, 4 or something like that. In fact, since the rate is 0.19, we are looking at this one event. Otherwise, this one event is also a rare phenomenon. If I change this rate to 0.09 or lesser than that, you won't see any ones in this sequence. Right, so this is what we have simulated for the next 30 days. What will happen in the room, whether the fan would come crashing down or not. So if I'm interested in finding the probability of the fan falling down twice in a day, so I am basically interested in finding out the density or mass. So twice in a day, comma, the parameter of the Poisson distribution. If I run this command, so the chance is 1.4% that the fan falls down twice in a day. The fan falls down once in a day, the chance is 15.7%. Right? And you have to understand the logic of this, because 15.7% may appear to be too large a probability for a rare event. But then this probability also depends on the rate at which the fan is falling down. The rate here is higher. So therefore, the probability is also coming out to be higher. If we had assumed a lower rate, then the probability would obviously be very, very low. So let's say we are interested in finding the chance of the fan falling down at most twice a day. So I would say I am interested in finding out the distribution function at most twice a day, and the parameter of the binomial distribution is this. Let me run this. So there is a 99 point this, that at most twice. So that means if at all the fan falls, it falls not more than twice with these respective. So more than twice a day. So it would simply be the probability of fan falling down more than twice a day would be simply this. If I run this command, so the chances are very, very low. Right? So if at all with this rate, if at all the fan falls down, it can at most almost surely fall twice and not beyond that, no more beyond that. Right? So, and finally, if we let's say we are in an earthquake prone region, and if we have multiple earthquake tremors in a day, And if I say that the chance of fan falling down was 48%, for example, then I am interested in knowing at most how many times such an event happened. So I would simply find out the quantile, Q poise 48%, and that's the parameter of my Poisson distribution, 0. So there is very little chance that the fan actually failed with this test.